Welcome! This video derives the natural response voltage of an RC circuit using separation of variables and direct integration. The derivation of RC, zero input response, ZIR, also called natural response, starts with a parallel RC circuit that has an initial condition capacitor voltage V sub C naught. The next step is to apply Kirchhoff's current law, KCL, highlighted in yellow. Insert the branch relationship equations for the resistor and capacitor currents into the KCL equation to get the homogeneous differential equation for natural response. Separate the variables and integrate to solve for the time-varying voltage V of t. There are several steps involving logarithms and exponentials. Before we go through the detailed steps of the derivation, let's look at context. Zero input response, which excludes any sources, can be part of a larger circuit analysis that does include sources driving the circuit.
Question: how do we get from the circuits with sources to the parallel RC that we use for looking at the zero input response by itself?
The answer is that we first turn off the sources of external current and voltage so that we analyze only the natural response. Turning off a voltage source is equivalent to making the voltage source zero value, which means a short circuit. Turning off a current source is equivalent to making the current source zero value, no current flowing at all, which means an open circuit. Removing the voltage source from the series circuit leaves a wire, resulting in a parallel RC circuit. Removing the current source from the parallel circuit makes the current source and its associated wires simply disappear. Starting the detailed natural response derivation steps, apply Kirchhoff's current law to the top node, summing the currents leaving that node. The red arrows indicate current moving out of that node.
There is only one voltage in the circuit.
The two marked voltages indicate reference polarities for the two circuit elements, the resistor and capacitor. The two currents are each positive relative to their voltage reference polarity. The currents are opposite one another.
There is also only one current in the circuit, and we know that current flows counterclockwise around the loop, making the resistor current positive and the capacitor current negative relative to the marked polarities. For more detail on current polarity, please view our video, RC Circuit Natural Response Polarity Reference.
The next step in the derivation is to replace the two current functions in the KCL equation with the current branch relationships for resistors and capacitors. The branch relationship for a resistor is Ohm's law. The branch relationship for a capacitor is the capacitance C multiplied by the time derivative of the voltage across the capacitor. Next, change the order of the two terms so that the derivative term is first on the left. Notice how the circuit variable in the differential equation is voltage. The voltage across the capacitor is also the voltage across the resistor.
By the way, it is also possible to derive RC natural response in terms of current.
Divide both sides of the differential equation by the capacitance C, placing resistance and capacitance together. This is the homogeneous differential equation for RC natural response. A homogeneous differential equation corresponds to an undriven circuit, a circuit with no sources. To start solving the natural response differential equation, move the voltage in RC term to the right-hand side, giving it a minus sign. Then divide both sides of the differential equation by V of t to group the voltage function term and the voltage derivative term together on one side of the equation. Multiply both sides by the differential term dt to move dt to the right-hand side of the equation, separating the variables. Now integrate both sides of the differential equation. Notice how the left-hand side has the term dv of t over v of t. To evaluate this integral, we can use the formula shown for the integral of 1 over x, which equals natural log x plus a constant of integration. Applying the formula for the integral of 1 over x, the left side of the differential equation becomes the natural log of the voltage function v of t. On the right side of the differential equation, the integral of dt is simply the time variable t. Each integral has a constant of integration, which can be combined together into one constant of integration, capital K. Preparing for upcoming steps, express the constant capital K as the natural logarithm of small k. This is still an unknown constant, regardless of the form. Next, recast the minus t over RC term as a natural logarithm. By definition, the natural log of e to the x is x itself. Therefore, we both exponentiate our minus t over RC term, and then we take the natural logarithm of that term. With all the terms in the equation now expressed as natural logarithm terms, we can combine the terms on the right-hand side by applying the formula for the sum of two logarithms. The sum of logarithms on the right-hand side becomes the logarithm of the product of k and the exponential term. Finally, we can exponentiate both sides of the equation to get an expression for v of t, where the constant k is still unknown. We can find the value of k by evaluating the equation for v of t at time t equals 0, where the exponential term goes to 1. We also know that at time t equals 0, the voltage is only the initial condition capacitor voltage V sub C naught. This means that the unknown constant K equals V sub C naught. The derivation is now complete. We have an expression for V of t, the voltage across the capacitor and the resistor. RC is the time constant tau for this exponential expression.
Thank you for watching and learning with us.